Right. See, when it comes to thermodynamics, what are, first uh, basic things we need to know? First is a nomenclature. There are very new terms that are used whenever we discuss about thermodynamics. So far, whatever we have been discussing, may it be chemical bonding, structure of atom, periodic properties, right? All these kind of topics, they deal with the microscopic level of atom. So we are trying to figure out, microscopically what is the subatomic particles present, their energies, and so on. Now, as we start going towards thermodynamics, here we are mainly emphasizing on the macro nature of the molecules, right? So we are not at all talking about an individual atom or in their behavior, their energy. No, we are talking about a group of particles together. What is the state it is adapting, whether it is in gaseous, liquid, or solid state, right? And that macro state of that macro nature of that particles, right, how it starts influencing the heat changes. So that means, in case if there is any energy, how it is transforming into heat, and from that heat, is there any other way it is transforming into work or any other energies which are usually observed in that particular state. So this is the main dynamics that we'll be learning in thermodynamics. Now, these are the terms that you need to be very familiar with yourself. One, what is a universe? In thermodynamics, every time we observe something, right, there is some change. There is um, maybe a gas which is present, correct? And there is some change in its temperature. So you are trying to observe the gas, not maybe visibly, but at least by the sense of maybe thermometer or something. You're trying to observe what is happening to the gas. So that space where you are trying to observe what's happening with the gas, that space is what we call it as the system. Okay. The space which is dedicated where you are trying to see the observation, that is called system. And everything around it, other than that system, is called as surroundings. Got it? So, in simple terms, if this is where you're making some experiment and you have some test tube or something in here, so this particular part is your system. Okay, so this is your system, and rest of the part which is not concerned to you here, I mean, that is not a part of a system. This is surroundings. So this is all surroundings, this is system, and together this entire space is called as universe. Got it? Now, system and surroundings are always divided by boundaries. Got it? And these boundaries could be real boundaries or imaginary boundaries. If they are real boundaries, which means there is, for example, if at all I take a glass of water and I'm trying to observe what's happening to the water's temperature and so on. Let's say this is how it is present. So now this part of the glass, including everything in the glass, that is my system. And now the actual uh, boundary, or rather I would say the entire periphery of this um, entire periphery of this glass is what we call it as the boundary. And this is a real boundary. But is it real at all the directions? Not necessarily. On top of it, it is, you can see it is open to atmosphere maybe. In that case, I can take it as a virtual boundary, that I can assume I'm making my system to end here. Anything above that is actually surrounding. I'm not bothered once it crosses that particular space, right? So up to this space, whether it is a real part or a virtual part, I will call everything that is present inside is a system. Anything outside that is surrounding. So if you notice from all other directions here, from the bottom, from the left, from the right, everything is a real boundary. And on the top, we have an imaginary boundary. Now, the real boundaries are of two kinds. Either they could be diathermic or adiabatic. Diathermic are those where it can conduct heat between system and surrounding. That means there is a transfer of heat between system and surroundings. Got it? So I can say there is some amount of heat which is going inside, because of which the temperature of the water might increase, or vice versa. It might be a hot water which is trying to interact with the surrounding gases, and release some heat out of it. Therefore, it is cooling. In that sense, you can see these particular walls or boundaries are diathermic. Then we can have adiabatic real boundaries as well. These are completely isolated, which means they are real boundaries, but they are very bad conductors of heat, like thermos, okay, thermoflask. They will not be able to transfer heat outside. So there is no heat exchange that is happening between system and surroundings. So those are adiabatic boundaries. Now, these are about boundaries. Now, there are three types of systems in general. Okay, the space which is under observation, those are of three kinds. One is an open system, then closed system or isolated system. We say system is open system if we are able to exchange mass with the surrounding, okay, as well as energy with the surrounding. So I can say in system there is a change in mass. It might be either gaining or it might be either losing. And same way there is a change in energy. So if mass and energy both are being exchanged with the surroundings, then we say it is an open system. If there is no mass being exchanged, but only energy is being exchanged with the surrounding, then we call it as a closed system. Okay. For example, if you have, you know, some food items in a box, a steel box, and you just packed it, which is very hot, got it? You are ensuring that none of the material from inside, no gases also are released outside, got it? But since the wall is diathermic, because the steel is something which is conducting, so what you could notice is that the energy is exchanging with the surroundings, but there is no mass that is coming out of the system. Clear? A pressure cooker, till the time there is, no whistle being blown, as long as there is no air coming out, you put it very tightly packed. So in that situation, if that is the area which you're observing, which is system, then that is a closed system. Open system is something which we are cooking on an open vessel. So there is a mass which is getting exchanged. There is energy also which is getting exchanged with the surroundings. Then we have isolated system where there is no mass being exchanged and there is no energy being exchanged. Any change that is happening within the system, right, is due to the parameters which are present in the system itself. So it is not getting influenced by any external heat, because it will not be able to exchange with it. So that is an isolated system. So there are three types of system: open, closed, and isolated. In open chain, mass and energy will exchange. Closed chain, only energy will exchange. In isolated, no exchange of mass and energy. Okay. What we do to apply the fundamentals of thermodynamics and to learn various parameters, we need to take one ideal system, and first we develop the formulations, everything around that ideal system. And then slowly we start generalizing, and we will take case by case. What if it is open? What if it is real gas? What if it is liquid? What if it is real ideal gas? This way we will start putting it as a cases on that, and then start modifying your parameters. So what is the ideal way of, you know, starting to frame all the thermodynamic parameters? So that system which is developed to understand all the parameters and, give definitions to all the parameters is this one, where we assume there is an ideal gas in an enclosed container where there is no mass being exchanged, only energy might be exchanged. Clear? So it is a closed system, right? And this particular closed part is movable. So it is movable. So it is a piston principle. It is based on a piston principle that it is able to move inside and outside. This is the most idealistic system to which we can make, which we can study and try to observe various parameters in it. Got it? And whenever we study about thermodynamics, we make a clear distinction. First, we will study this entire closed system of ideal gas enclosed in it, wherein there are no chemical reactions taking place. So we assume the fact that there are no chemical reactions happening. So that is our first part of thermodynamics, right? So we are assuming no chemical reactions are taking place, only physical changes, pressure change, volume change, temperature changes. These are the parameters which are changing, but there is no interaction between the particles to change into something new. All right. Then we study the second part of thermodynamics, where again we'll take a similar system, and then we assume that there are ideal gases which are making chemical reactions. Based on that, again we'll study new parameters and we'll try to see how those are varying. Correct? So I hope all of you got this idea. What are the two parts which we'll be learning? Okay. Next. Next one is about the state of a system. Once we have decided what we are studying, that we are studying about the ideal gas in an enclosed container with a movable piston, that is our ideal system. In that, we are trying to figure out what is the state of that system. State implies that what are the parameters that are associated with it. For example, if it is a liquid state, solid state, or gaseous state, it is all defined on the basis of these four parameters, which includes pressure, volume, temperature, and number of moles. Got it? Now, to measure this, like what is the pressure, what is the volume, what is the temperature, and number of moles? See, if you may have remembered, in gaseous state also when we learned, if you are measuring the pressure of a substance or a gas, maybe inside a system, here you are trying to figure out what is the pressure in this particular system. What is an essential condition? The essential condition is this system needs to be at equilibrium to measure. Okay. If there is a continuous variation of pressure, I can't figure out what is the average pressure at a particular point of time. Therefore, that system has to reach some kind of equilibrium to measure these parameters: pressure, volume, temperature, number of moles. To do that, again, we are trying to come up with another case here, wherein we take one ideal gas in a container and we take another ideal gas in the same container, and both of them are separated by a moving separator. Okay, so that means it can be like a moving piston in a compartment. Clear? Now, this gas A and gas B, assuming both are ideal, right? Assuming both are ideal. In that case, suppose if on both sides, correct? if on both sides the pressure becomes equal, then do you think this separator will move? No, right? It will remain at equilibrium. So that means we say in this system, the equilibrium has been attained. What type of equilibrium is this? If there is physically observed bodies which are not moving in the system, that means we say it has achieved physical equilibrium. So if this separator is not moving, I would say a physical equilibrium has been achieved. And when would that happen? Usually this will happen when the pressure from all the directions are same. So you can see pressure here is PA and pressure here is also, sorry, this is PB and PA, and PA and PB are equal, then we say system is under physical equilibrium. Clear? Now, second thing, if this moving separator is a diathermic wall, if it is a diathermic wall, we can expect that there could be heat exchange between two chambers A and B. This is a chamber A, chamber B. Between these two, there could be a heat exchange. And imagine as the heat keeps exchanging, what is the parameter that changes? When there is a heat being gained or a loss, the parameter associated with heat is temperature. So there is a gain in temperature or loss in temperature numerically. Thus, after heat exchange, when temperature on both the sides becomes equal, right? Then we say the system is at thermal equilibrium. Now, is it necessary to have physical equilibrium to attain thermal equilibrium? No, these two equilibriums can exist independently. Okay, these two equilibria can exist independently also. But usually, if you are taking a diathermic wall and there is a movable separator, chances are it would attain physical equilibrium, and maybe after some time it will attain thermal equilibrium also. And by chance, if there are any chemical reactions happening on both ends, and the chemical reactions has either completed the reaction or they have attained chemical equilibrium, either there is a completion or it is at the stage of a chemical equilibrium on both sides. Why? Because if chemical reactions are happening, we expect at some point of time the total number of particles will remain same. That means if you have taken, right, I mean not same, sorry, they have reached constant value. If there are certain number of particles here after the chemical reaction, if it has reached to a point where it has uh, some n number of particles, then that value, if it is not changing and it remains constant, then we say this has attained this side and this side, chemical equilibrium has attained. Now, if all three equilibriums have achieved, then we say the system is under thermodynamic equilibrium. What are the equilibriums we should have? Physical, thermal, and chemical. If all these equilibriums have been achieved, then we say thermodynamic equilibrium have been achieved. And only when thermodynamic equilibrium is achieved, we will be able to measure pressure, volume, and temperature of a state. So I suppose all of you got this idea. What's happening here, right? Now, pressure, volume, and temperature can be measured only at thermodynamic equilibrium. Okay. Now, parameters that we are measuring in this system, right? They are of two types of variables. In fact, pressure, volume, temperature, these are all variables, right? Those are defining the state, but their value might vary and they are dependent on each other. Clear? Such types of variables which are defining the state are called as state variables. These are called state variables. And state variables depends on the initial and final state of the system, and they are independent of what kind of a path we are going through. Then we say it is a state variable. Okay. So pressure, volume, temperature, if originally it was at, let's say at a state A, and from a state A now it has reached to state B, so then we are not worried about what is, by what path it has come from A to B. Then we say these parameters which are independent of the path taken, those are called state variables. Okay. For example, suppose if you are climbing, if your classroom is on the fifth floor and you are climbing all the stairs to reach your classroom, correct? So let's say on doing so, you have done some amount of work, correct? Your body has, you know, your body did some work to reach that fifth floor, right? But at the same time, there is a elevator just next to the stairs. If you take the elevator, that's another way of reaching to the same class. Now, in both cases, you must have done some work, but you can clearly make out that the work that you have done to climb up the stairs is more, right? As compared to that of what you did in elevator. Okay. But whether you take stairs or whether you take elevator, once you reach to a certain height, which is the fifth floor, isn't your potential energy same? Because potential energy only depends upon the position where you are. It does not depend upon what kind of a path you have taken to reach that position. Is that clear, everybody? So when it comes to potential energy, it is not asking you, hey, did you take stairs or did you take, you know, uh, escalator, or did you just fall off from the top? No. Clear? As long as you are at a certain position, your potential energy is fixed. Such kind of parameters which are independent of path, independent of the event which you have done, that is called as state variable. Clear? And pressure, volume, temperature, all these are state variables. Okay, just a minute. Clear? So pressure, volume, temperature also does not dependent on what kind of a state, how did you achieve, whether you heated the gas, whether you have actually pressurized because of which the temperature is increased, doesn't matter. Okay, whatever the act you have done, whatever the event you have done, if there is some change in the pressure, volume, temperature, that is a new state, irrespective of how it is achieved. Okay, so variables which are independent of the path taken are called state variables. Okay, clear? They do not depend upon the path taken. Understood? Now, pressure, volume, temperature, we have learned that they are independent of path taken. Along with that, these are the new parameters that you need to slowly start getting habituated with. Okay. Easy way to remember is this. Remember it this way. Usha G. Okay. USHAG. U as in internal energy, entropy, enthalpy, Helmholtz energy, Gibbs free energy. All these are energy terms, different forms of energies. Okay. The basic ingredient of that energy is heat only. Okay. Heat in different situations. Those are all have different names here. Understood? Again,
Sir, what
internal
does S stand for?
entropy. U is internal energy, entropy, enthalpy, Helmholtz energy, and free energy, Gibbs free energy. Got it? We will be introduced to one by one. Don't worry about it. You will get slowly. You will get an have idea about all these parameters. But the easy way to remember is this Ushaji PVT. Clear? All these are state parameters. Like I said, work was something which was entirely dependent on path, isn't it? Whether you're taking stairs or whether you're taking elevator, that was very important decision. That changes the outlook of the work. Therefore, work is such kind of a parameter which is highly path dependent. Along with that, heat is another parameter which is highly path dependent. Okay, how much heat that is changed, it highly depends upon what is the path that you are giving. Got it? Okay. In simple terms, the heat given by maybe, suppose you're supplying heat by a gas stove, correct? So that might, the time spent to give that energy might be same as compared to what is the energy that you are getting it from sun. But the amount of heat that might be given might be different in both the situations. So it all depends upon what path you are taking, especially to uh, observe the heat. Hence, work and heat are the two main parameters which are path variables. Now, mathematically, what you need to learn. See, if there is any x parameter, a new parameter that is given to you, and you need to figure out whether it is more path related or whether it is more state related, then you should be able to mathematically prove it that it is actually a state variable or a path variable. So since state variable looks relatively more easy to define because it only depends upon initial and final condition, so we can actually prove whether a function is state variable or not. To prove whether a function is state variable or not, we will look into three set of mathematical uh, derivations. One is the cyclic integral value, cyclic integral value of any change in a state function has to be zero. Got it? That means if you are integrating, suppose if you are starting at a point A and if you are coming back to the same point A, isn't it? Right? You went to all these different path and you are coming back to the same path here, right? I mean, sorry, same point here. So imagine if the initial pressure was P. Now, after all the change, again, you'll come back to P only, right? So what is the difference? It should be zero, right? That's what mathematically we are denoting. So this circle means it is a cyclic integration. So when you make a cyclic integration of a function and then you will get it as zero, that means the function which you are integrating is a state function. This is one way to uh, confirm that we are talking about a state function. Next, the other more interesting way is using Cauchy's equation. So as per Cauchy's equation, suppose if you have a function which is a state variable, then if you differentiate that function with respect to some variable y, let's say I have a variable, pressure, and I'm trying to differentiate first with respect to temperature, and then I'm differentiating again that with respect to volume. Got it? So here pressure is the state function which you are assuming, and temperature and volume are variable parts, whenever the pressure is changing. And as per Cauchy's equation, if this will be same as the first differentiation with volume and then differentiation with temperature, if you are able to write something like this, and if they both are equal, then we say this particular function fx is exact function. In in calculus, we call it as exact function. Got it? And exact function is always a state variable. It only depends upon initial and final condition. Okay? And if f of x is an exact function, right, we should be also able to write the change in that function, any small change in that function. That means it depends upon initial and final condition. It should be we should be able to express them in multiple uh, in multiple variables using this partial differentiations. Correct? See this best example here. For example, U, which is an internal energy. Internal energy is a state function, but it can be expressed with another two state function, which is T and V. So imagine internal energy is a function of T and V. Here, U, T, V, all of them are state functions. Then, according to the exact function, uh, according to the exact function equation, any change in the variable of internal energy, which is du, will be equal to partial differentiation of that u with respect to v at constant temperature. In fact, when we are using the word partial, means you are only using one variable to change. Other variable has to be kept constant. So, differentiation of u with respect to v, partial differentiation, which is happening at constant temperature, into dv plus differentiation of u with respect to t happening at constant volume into dt. If you're able to write something like this, that means it is an exact function. So there are two ways to denote. One is Cauchy's equation, Cauchy's equation. The other one is exact function equation. If you are able to prove any one of these, that this is something which it can exist, or this is something which it is happening, then I can say that function you are defining is a state function. Now, suppose the same U is a function of pressure and temperature. Again, this time you can write the same thing instead of volume. It will be with respect to pressure. And let's say U here is a function of number of moles and volume. So you can write that in terms of number of moles and volume. Here, internal energy, number of moles, volume, all of them are state functions. Correct? Everybody? Let me show you some example to understand that more easier. Check this way. Suppose I need to prove that pressure is a state function in PV is equal to nRT. PV is equal to nRT is an ideal gas equation. And I want to prove that pressure is actually a state function in this. So what I can do? First, because pressure is dependent on volume, temperature and number of moles, I would assume P is equal to nRT by V. So first I'll differentiate this with respect to V. Okay. And only V. This is actually this is partial differentiation only. I have not written it that way, but please understand that it is partial differentiation. So what do I get? I'll get this as minus nRT by V square, correct? If you differentiate that with respect to V. And then differentiate, that with respect to T. This part, you differentiate that with respect to T. So it will become minus nR by V square. And do the same thing here first with temperature, then with volume. So if you differentiate P is equal to nRT by V with respect to temperature, it will become nR by V. And thereafter, you differentiate that with respect to volume. Again, you will get it as minus nR by V square. So you notice that both the values are coming same, which proves that pressure is actually a state function in an ideal gas. Clear, everybody? Yeah. So most of the time, this is much easier and convincing way to express that a function is a state function or not. Okay, right. Now this exact function becomes very, very useful, especially when you have uh, multiple variations of a functional group. That means you're trying to apply, you know, uh, we are trying to calculate internal energy, let's say, in real gas, in ideal gas, in liquid system, in a solid system. In that cases, to express the exact equation of the internal energy change, this will be very, very useful. As we go ahead, I'll show you how it can be useful as well. Now, notice, since we are talking, like I said, thermodynamics is mostly about the macro properties, and we are not emphasizing anything on the micro properties of the particles. These macro properties of particles in a system are of two kinds. One is extensive, the other one is intensive property. Extensive property is something which it depends on the amount of the substance taken. If it is gas, then how much gas you have taken. Quantity can be measured in terms of mass, volume, right? But can we measure the quantity in the terms of density? No, right? Because density, whether you take a small portion of gas, whether you take a large portion of gas, okay, density only depends upon mass by volume. So it is not a quantity term. Clear? It is more of a quality term, whether it is high density, low density, right? That's what we can express. But quantity is something which is increasing in its dimensions, like volume or its mass. Then we say it is extensive. All these parameters, like U, S, H, A, G, then volume, mass, and number of moles. These are all those type of parameters, state parameters, okay, which are extensive properties, which show extensive properties. Then we have intensive property. They are independent of how much amount of mass of a gas taken, volume of a gas taken, or number of moles of a gas taken. So these parameters includes pressure, temperature, density, refractive index, right? Melting point, boiling point, molarity, any concentration term, electromagnetic force, okay, that is EMF, voltage, right? And now notice this one. All these extensive parameters or extensive property parameters, if they are being divided by any intensive property, okay, then this results in intensive again. So we can say extensive by extensive is also intensive, and intensive into extensive will be equal to extensive. Extensive into extensive is extensive, and intensive into intensive is intensive again. So here what I can say, extensive by intensive is leading to what? Intensive. Clear? So you can notice that this is extensive divided by intensive part. So what is it becoming? Again, intensive. Okay. 1 minute. Let me see this. So let's take intensive divided by intensive here. Sorry. Here it should have been I here. I into I is E. Okay. This I'll delete it off. Yeah. Right. So you put it this way. Okay. Clear? So extensive by extensive is also intensive, and extensive by intensive. No, no, no. This one I put it wrong. This one I have written it wrong, but sorry. Here. Now this is correct. Yeah, now it's fine. See, this is an extensive part. Enthalpy is an extensive part. N is also an extensive. If you divide both of them, what are we going to get? Intensive. Okay. So therefore, extensive is equal to intensive into extensive. So this is what it is. Clear? Any extensive into extensive is extensive. Intensive into intensive is intensive. Got it? Now, just to show you this idea, suppose I have a room in which there is a gas present, and suddenly, if at all I make a partition between the room, you don't see any change in the pressure here and here, right? The pressure will still remain the same, correct? And if you made one more compartment here, here also the pressure of the air here, here, and here will still remain the same. Okay, because pressure does not depend upon how much is the quantity of air which you are taking. Okay, but what about the volume? Volume is decreasing every time you change the parameter here. Every time you make partition here, the volume will change. Volume wherein the particles are occupied will be different now. Okay, so that's why these type of parameters does not depend upon the quantity. That is called intensive property. Clear, everybody? What are intensive and what are extensive properties? Next. The next term, very important term, is internal energy. Okay. It is the total forms of energies that are present in a system. And what are those total forms means? Suppose, let us start with a simple gas only. Because like I said, I keep on moving around and come back to that same ideal case only. Ideal case is a gas in an enclosed closed system with a moving piston. So if suppose there is internal energy to be found, so since particles inside them are moving, they possess kinetic energy, and there might be interaction between the particles which tells us there is potential energy. And in fact, within the molecule also, between the particles also, there are bond energies, and within the bond energies also we have electrons present, and electrons will have again some kinetic energy and potential energy, isn't it? Like that, from the microscopic level of energies to the macroscopic level of energies, every energy that you add it, that total will become internal energy. And of course, it is not practically possible to calculate the internal energy, isn't it? And I can say internal energy is summation of all the kinetic energies and all the forms of potential energies. And when I say kinetic energy is always observed in three forms. One is translational, rotational, and vibrational kinetic energy. Okay. Translational as in a particle is moving from one point to the other point. So what is the speed with which it is moving? What is the kinetic energy it is carrying? That particular discussion is about translational kinetic energy, right? If a particle is moving from a point A to point B, but while moving, it is also rotating like this. Let's say if it is rotating like this, and then it is rotating like this, then it is rotating like this. And so it is moving like this. It is going towards a new position, but also starting to rotate like this. Then, along with having a translational motion, it will also have a rotational motion. And this might also happen while particle is moving. A particle might be something which is a molecule, which will have atoms, and atoms continuously keep vibrating. So this is the bond, right? Wherever there is a bond, atoms are vibrating like this. So this vibration is also a part of kinetic energy. So therefore, three types of kinetic energies will always exhibit. One is translational, then we have rotational and vibrational. Okay. Then what are potential energies? Like I said, any form of electron-electron repulsions, electron-proton attractions. Okay. And then you have pi electron, nuclear charge and electron. That is an attractive uh, potential energy. These are repulsive potential energies. This is attractive. This is repulsive. So any interaction between the atoms, between the molecules, within the atom and within the molecule, they all, including summation of all of that, is potential energy. Okay. So adding these two, we will get the internal energy. Now, internal energy has all these parts: kinetic energy, potential, vibrational, Then again, you will have this as the electron internal energy, rotational energy, nuclear energy. So all of these including, we will get internal energy. Now, the absolute value of internal energy cannot be calculated or measured, but we can say it can be written in terms of individual types of internal energies. Now, the most contributing energies here are, you know, electronic energy, then vibrational, rotational, and translational. Okay. That means here we are talking about electronic level, electron repulsion, electron proton attraction, all of that. So that would be the highest contributor to the overall internal energy. But if you are not interested in internal energy, and your interest mainly lies between what is the difference in the internal energy, then I can say the difference in translational motion is more than difference in rotational motion, then vibrational motion, then electronic uh, effects of delta U. Correct. So here we assume that this vibrational motion's internal energy is only contributing at high temperature. Otherwise, vibrations are not much effective, okay, to be contributing to the overall internal energy. Okay. So even if there is any change in internal energy, you will hardly see any change in the vibrations at lower temperatures. So therefore, this would be least contributing here. And electronic repulsions, attractions, that is also least contributing here. The difference is least contributing. So mainly the difference comes because of the translational and some part due to rotational and very, very less part due to vibrational. Okay. So now delta U is equal to delta U trans plus delta U, rotational. And this is only taken at normal temperature. At high temperature, I need to consider vibrational internal energy change as well. Okay. Next, let me come across the other important term known as heat capacity. Heat capacity means how much amount of heat that needs to be sent or to extract to change the temperature of that system by 1 unit. Okay, you are just trying to change the temperature of that system by 1 unit. Then we call it as heat capacity. So heat capacity are mainly material dependent and process dependent. Whether the material what we are using, whether it has more heat capacity or less heat capacity. And then it is a process dependent. What type of process in which you are checking out the heat capacities? Is it isothermal, adiabatic, isochoric, right? These type of processes, they all vary the heat capacity. And heat capacity is infinite during phase change. Okay. During the phase change means change from solid to liquid or liquid to gas, or any of those changes are called phase changes. So if there is any phase change within the molecule, so in that case, heat capacities is infinite. So in such case, delta T value, you can see uh, what happens here. Heat capacities. See, usually how do we define this? Heat capacity C is defined as how much amount of heat that is being given or dissipated to change the temperature by 1 unit. Okay. And if there is if there is a substance in the system where, uh, if there is a substance in the system, let's say, and you are trying to verify how much amount of heat it will sustain. So that in that case, what do we check out? Q by delta T. Correct. Now, If you are doing it for different types of heat capacities, we will have different names associated with it. For example, if you write only heat capacity, nothing else, then we write this as, small c here, small c, which is equal to how much amount of heat that is being given to change the temperature. Similarly, we can have specific heat capacity. In physics, you will be using this, quite often. S will be equal to Q by N into M into delta T. So why M? Okay, because now we are doing it for per gram or per kg of, you know, total heat. So that is called as specific heat capacity. Then we also have molar heat capacity. So it is usually represented as Cm, which is equal to heat given by, instead of mass, now it will be number of moles into delta T. Okay. So remember, three types of heat capacities we have: only heat capacity, specific heat capacity, and molar heat capacity. Okay. So if you are writing it this way, suppose if at all I take it at constant volume, that means I'm trying to increase or decrease the temperature of a system at constant volume. And if I'm doing it constant volume, let's say the heat given or taken is QV. So QV divided by delta T into N. So let's say I write it as N here. So then that should be equal to CVM. Why CVM? Cm means molar heat capacity. And along with that, it is happening at constant volume, right? So that's why a new terminology is given, CVM. Okay. Heat capacity at constant volume, and it is molar heat capacity. Okay. So that will be called as molar heat capacity. Got it? One second. Now, let me talk about what is thermodynamics first law. Okay. According to thermodynamics first law, right, any change in the system which we are measuring as a form of internal energy, okay, right, thermodynamics first law, we are saying any change in the system's internal energy is a consequence of heat transfer and work that might be done. It could be either by the system or it could be on the system. And Q is also heat that is being given to the system or heat taken away from the system. Just think logically. Okay. You have a certain box of energy here. Okay. So this is a system, and this system, there is some amount of energy present. Correct. Now, out of that, there is some amount of work that is being done. So it was supposed to be this full initially, because this has, let's say, total amount of energy inside. And from here, in case, if at all I lose some small amount of energy out of it by working, okay, due to work, it has lost this amount of energy. This I am symbolizing with a different color. Correct. And there might be loss of heat also. Let's say from here, there is some heat being lost as well. So which means first I will have some work which is being lost, and then we have from here, let's say there is some amount of heat that is being lost. So this is, let's say, work, This is, let's say, heat. So because of which, again, I'm able to see some more different forms of energy has been consumed here, like this. And then we had this work done, which has been changed. And moreover, whatever the initial amount of energy was, this is what it is. So initially, let's say you had an energy U, okay, or U1. And now what happened? Here it has become U2. Here it has become here it has become U3. Okay. Now this is the initial condition. This is the final condition. Correct. And since internal energy is a state function, so whatever the change that might have happened in the internal energy, what is the consequence? It is because some amount of energy was utilized to do some work, and some amount must have been released out in the form of heat or accepted in the form of heat, either ways. Okay. Here, since I'm showing it as a loss, you can imagine as if this Q is a lost heat and work is a lost work, which means system has only done the work on it. So this representation, that is the change in internal energy, is a sum of work done and heat evolved or involved. That is called as thermodynamics first law. Clear? So Q plus W is equal to delta U. And imagine if you are operating at this as constant volume. If you are doing it at constant volume. Now, what is this work exactly? Work is something, you know, this W is an expansive work. Expansive work means where if you are doing some work, there should be some change in the volume of the system. Then we say it is expansive work. Correct? So there are many such processes where we try to do at constant volume. In case if at all you do at constant volume, that means volume is not changing. If volume is not changing, work cannot be done. If work is happening, there is some amount of change in the work. That means there must be some amount of volume loss or gain that should be uh, pointed out. But that is not we are doing. So W is equal to 0. So Q plus W is equal to delta U at constant volume. I can say this is at constant volume. At constant volume, QV is equal to delta U. QV is equal to delta U. And you know that what is heat capacity, which is equal to delta U by delta T. Okay. And delta U by delta T can be written as du by dt, or since you are operating at constant volume, I can write it as du by dt at constant volume. I think this part is clear. I'll be able to write this as heat that is being given, right, at constant volume will be equal to delta U. And that divided by delta T will give you this one. And this was for 1 mole. If at all we have n number of moles, you have to divide that by n. So therefore, for n number of moles, it will be du by dt, got it, at constant volume is equal to number of moles into heat capacity. Okay. So from here, what we can write? So from here, I can write this as du will be equal to NCV delta T. So this is a very, very important formula for us. Delta U, that is change in internal energy, is equal to NCV delta T. Clear, everybody? Now, heat capacity CV is a fixed property of a gas and can be used in any process. That means once a heat capacity of an, let's say, nitrogen gas is decided, whether it is in process 1 or whether it is in system 1, system 2, anywhere, the heat capacity of that gas is defined and that cannot be changed. Got it? That is what it meant. So heat capacity is a fixed quantity. Next, if U is a state function and it depends upon state variables like P, V, T, Let's say it is dependent on temperature and volume. Then we can write this equation: du is equal to dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dv. Okay. Now, just now, above, if you notice, du by dt at constant volume, we can replace that with ncvm. So this entire value can be replaced as ncv delta t. Henceforth, the cvm, because every time we have cvm, instead of writing this, we can simply write it as cv. Similarly, cpm, we can write it as simply cp. So that means it is at constant volume process. This is at constant pressure process. Okay. So du can be written this way, and that will become ncu delta t. So du by dv into dt into dv. This is the general equation of internal energy change, everybody. This is called general equation of internal energy change. Now notice, what is first equation of state? First equation of state is expressing dou u by dou v at constant temperature is equal to T into dp by dt at constant volume minus P. Now this we don't have to derive it. Mathematically this has been already derived. So we just need to take up, for application purpose only. We don't have to worry about derivation. But my request is, if you could remember this part, it helps you immensely mathematically when you are solving it. Okay. In whichever question you will apply, it becomes very easy to understand what exactly is going on mathematically. Okay. So this is called first equation of state, which is expressing internal energy change with respect to volume at constant temperature, right? And in that case, which can be written in terms of temperature and pressure this way. Let's try to prove this. Find the value of du by dv at constant temperature for ideal gas. So du by dv. So first you know that pressure is equal to nRT by V. And suppose if at all I differentiate that with respect to temperature at constant volume. So I can write, because it is at constant volume, we learned that it will be nR by V. Correct? This will be nR by V. And T into this factor, we learned it as nR by V. So let me write down that T into this entire thing is nR by V. And that minus P. So minus P. So what will that make it? 0. So that means for ideal gas, delta U will be equal to NCV delta T. Okay. Because this factor is coming out to be 0, which means this factor is not accounting for any contribution if it is ideal gas. Okay. So I want all of you to just take a minute's time, go through from here, from first law of thermodynamics till this part, that how did we prove that du by dp at constant temperature is 0. Okay. Please take a minute's time, go through it once. Imagine I need to find what is the value of du by dv at constant temperature for a van der Waal gas. Van der Waal is a real gas, right? So for a real gas, what is the equation now? It is not simply PV is equal to nRT. We know that pressure will be equal to nRT by V minus NB minus A N square by V square, because the actual equation is P plus A N square by V square into V minus NB is equal to nRT. This is the van der Waals real gas equation. And if you write everything in terms of pressure, this is what you will get. And now to get dou u by dou v in at constant temperature, I'll be using the support of first equation of state. And within first equation of state, one of the important part that I need to first derive is dou P by dou T. So since I got the pressure equation, let me write down that what is dou P by dou T. Dou P by dou T, this is all constant values. So that will become 0. So this will be differentiable, which will become nR by NB, V minus NB. And for that, we need to multiply T and subtract it by P. So when you multiply T, this will become nRT by V minus NB. And what is P? P is this entire thing. So again, I substitute that value. So you can see this nRT by V minus NB, nRT by V minus NB, these two will get cancelled. What is left? A n square by V square. That is the part which is left. Okay. And now this entire thing is dou U by dou V at constant temperature. And that is equal to A n square by V square. A, N, V, all of them are positive values. So therefore, this value is greater than 0. So from here, what we have learned for real gases, remember everybody, for real gases, if the volume increases, the internal energy always increases. So that is what it tells us. But it should be at constant temperature. So at constant temperature, as the volume increases, internal energy will also increase. Okay. But for ideal gas, what did we learn? For ideal gas, what we learned is that integral du, which is equal to T1 to T2 NCV dt. So if I integrate that, you'll get this as delta U is equal to NCV delta T. For ideal gas, at constant volume, this factor is 0, right? So therefore, delta U is equal to NCV delta T. But for ideal gas, delta U will be equal to NCV T1 by T2, and this entire factor, go back to this equation. This is that we have. Now this we just learned that du by dv at constant temperature, we got it as a n square by v square. So I can write down that a n square by v square into dv integral v1 to v2. Okay. So this is the equation of delta u for real gases. Okay. For ideal gas, we'll only get NCV delta T. But for real gas, we'll also get this particular factor. Okay. So please go through it once. Please check if you have understood how we have derived delta U for real gas. This is delta U for ideal gas. This is delta U for real gas. Clear? Right. Now, we learned one thing that for an ideal gas, delta U, which is equal to NCV delta T. For real gas, it is NCV delta T plus AN square by 1 by V1 minus 1 by V2. This is the factor we learned. What about if there is something about liquids? In case if we have liquids, then what do we write? See, go back to the original equation. du is equal to del u by del v, del u by del t at constant volume into dt plus dou u by dou v at constant temperature into dv. Okay. Since when it comes to liquids and solids, do you think liquids and solids can compress? No, right? Their compressibility is very, very low. Okay. Since the compressibility is very low, do you think this factor is anywhere contributing? No, this factor is hardly going to contribute. Is that clear, everybody? Since there is no volume change, this factor does not contribute at all. And second thing, if you know what is the first law of thermodynamics, delta U is equal to Q plus W, and W is only operatable if there is a change in volume. If the volume is not changing, especially for liquids and solid, this will also be cancelled out. So which means whatever the heat that you are supplying is only changing internal energy, which means the delta U, so the du which we are writing at constant temperature, because the heat capacity now at molar heat capacity now is defined as Q, that is being given with respect to number of moles into delta T, correct? And C, Q is equal to NCM into delta T. Now this does not have to be necessarily specified as constant volume. Even when you boil the water, right? I mean, sorry, heat the water or cool the water or something, the volume changes very, very small. Okay, that's a very small change. So therefore, heat capacity, the amount of heat that is being given, right, will be almost same as that of internal energy change. So then I can write delta U is equal to N Cm into delta T. And since this second factor is not at all contributing here, so you can say delta U is equal to NCm delta T for solids and liquids. For solids and liquids. And that's what I have mentioned here. For solids and liquids, it is N C delta T, correct? Here, whether you operate at constant volume, constant pressure, everything is same for solids and liquids. Okay. So heat exchange at constant volume is always equal to the magnitude of internal energy. Clear, everyone? Right. Now, molar heat capacity at constant pressure. If it is at constant pressure, then we will write some terms like Cp is equal to Cv plus R. How do we get that? We'll discuss it now. Okay. Cp by Cv is Poisson's ratio and Cp is equal to Qp by delta T. How do we get that? Where is it useful? We'll discuss it. Okay. But before getting into this dynamics, that what is molar heat capacity at constant pressure, how it is related with constant volume, right? So first we need to understand the next term, clear? That is about how internal energy for an ideal gas depends on temperature only, temperature only. See, for an ideal gas, the total potential energy change is zero, correct? Why? Change of potential energy. Reason being, between the particles there is no interaction. And since thermodynamic is mostly about the macro changes, internally how the particles are, what is their bond, that is not going to change if at all we are heating or, providing heat or work done, something like that. That is not going to change much. So therefore, since intrinsically nothing is changing, so any change in potential energy is zero, which means for an ideal gas, any change in kinetic energy is a change of internal energy itself. And kinetic energy usually has three parts, like I said you. There is translational part, rotational part, and vibrational part. Okay. And as per KTG, that is as per kinetic theory of gases, as per kinetic theory of gases, we can assume ideal gas particle has a point mass, like a point like this. Just gases have like a point. We are not saying that it has a specific shape like that or some kind of a shape like this. No, we are assuming just it is like a point, right? If you have just a point and extremely small size of it, can we attribute anything to the rotation? No. Can we say something as a vibrational kinetic energy is applicable to it? No. So the only form of energy that is applicable for point particles or point masses is only translational energy. And in KTG, kinetic theory of gases, we learned that the average kinetic energy of the total average kinetic energy. A minute here, I have to write kinetic energy total. Total kinetic energy of n number of moles of gases will be equal to 3 by 2 nRT. Correct? Now, since this summation of potential energy is 0 and U is equal to summation of kinetic energy, so that means any change in internal energy should be change in kinetic energy and change in potential energy. And we learned that change in potential energy is almost 0. So therefore, delta U will be equal to change in kinetic energy. And kinetic energy only depends upon two factors, number of particles and number of moles and temperature. And since we are not changing number of moles, so the only factor that is changing is temperature. Hence, delta U can be written as 3 by 2 nR delta T. Okay. So from here I can say that any change in the temperature is directly impacting the change in internal energy. Hence, for an ideal gas, internal energy is a function of temperature. Okay, for an ideal gas, internal energy is a function of temperature. So you can see at constant temperature, delta U will become 0. If this is 0, then delta U will become 0. Okay. So I think the concept of internal energy is clear to everybody, and how it is related in terms of ideal gas, real gas, uh, solids or liquids. And moreover, if at all you are representing for an ideal gas, we can directly write U as a function of temperature. That is the proof. This is the proof for that. Now, what is heat? Heat is the energy transferred due to difference in temperature between system and surroundings. Okay. If there is any temperature difference and we have a diathermic wall, then the energy which is transferred is called as heat. Heat always transfers from high temperature to lower temperature. Okay. What is work exactly? Work, by definition, it is opposing force into displacement. Okay. For example, if you have something of this sort, right? So imagine I have uh, a block here and we are trying to push this block. Okay. But this surface has no friction on it. And somehow, as I start pushing from here, I'm able to take that block almost up to this distance. So it is covering a distance d. I'm covering a distance d. Clear? In that case, what is the work as a person who is pushing this block? How much amount of work I might have done? Okay. And work done, what is the definition just now we learned? Right? Opposing force, opposing force multiplied by this distance. And how much is the opposing force in this case? The opposing force in this case is 0. So the work done in this case is 0. Why? See, when you are trying to move the block, if there is no friction on the ground, right? If there is no friction on the ground, is there any other possibility by which there is any kind of repulsive or reactive force coming from the block? No, right? So it is smoothly moving. So just you touch it, it will start moving. Correct? So if I'm working to move a block from one position to the other position, without friction, there is no work. But if there is friction, then there is definitely opposite reactive force. And that is that force we are talking about. Opposite reactive force into displacement gives work. So work is an opposing force into displacement. For example, if I take our ideal condition, which is ideal gas in a closed container with a piston on it, and imagine outside there is vacuum. There is nothing. In the surroundings, there is nothing. Everything is vacuum. Then what would happen? Then gas will start expanding because there is an ideal gas here with some pressure P. Outside there is no gas with zero pressure. So what should happen? There is a pressure difference created here. So due to this pressure difference, the piston will start expanding. So X will convert into X plus delta X. X will convert into X plus delta X because this length of the uh, column will increase. But is there any work that is being done just because volume is increasing? Is it necessary that work has to be done? Not necessary. Remember that Every time volume is increasing does not imply work is done. Work is been done. Okay. In this case, work is not done. Work is zero. Why? Because externally there is no force which is stopping it. And work is always done against the external force. Okay. Now notice this one. If you have X here, outside there is some ATM pressure. That means there is some atmospheric pressure here. And then there is again some amount of X which is developed. So yes, outside there is some pressure. That means there is some force which is opposing it. And yet you are trying to overcome that by working. Now this time gas will work. So work of the gas is equal to opposing force into delta X, because this much amount of change of length that has been observed. And force, opposing force can be written as pressure into area, cross-sectional area. A represents what is a cross-sectional area. P represent opposing force, because force is always equal to pressure into A. So therefore, pressure into A into delta X. What is A into delta X? This is area of the cross section into some amount of delta X that is been covered. So this is giving area of the cylinder, and area of volume of that cylinder, and volume of the cylinder is delta V. So A into delta X is equal to delta V. So work done, we get it as a formula that it is equal to P external. That means how much pressure externally it is been opposing into delta V. So this is work done. Clear? Now, this might so happen if the external pressure is more. Okay, if the external pressure is more, that might push the piston inside. So which means even though there is a work being done by the particles, it is not overcoming, right? It is not able to overpower the external pressure. That's why it is suffering a loss in the volume here. So again, the formula remains the same. Work done is equal to P ATM into delta V. Okay. Now, what is the general formula for work? So integral 0 to W dW is equal to minus P external into dV. So this would be P ATM into delta V. In this case, it will become P external into delta V. This is a general equation. Why is this minus? Okay, why this minus? This is a convention that we use in chemistry. Okay, now whenever we talk about any thermodynamic process from chemistry's point of view, what we are trying to do is that we are always being a part of the system and observing. In physics, it's exactly different. In physics, you are an observer who is outside the system, not inside the system. And then you are trying to observe what is happening to the system. In chemistry, we will not do like that. We will sit in the system and then observe what are the changes happening around it. So therefore, what you will see, as per chemistry's convention, observation is always inside the system. If it is inside the system, you notice any loss to the system, right, which is done by the system. That means how much is the loss which is done by the system, or dissipated or released by the system. Okay, dissipated or released by the system. That is a negative change here. That is a negative change. Anything that is done by the system, that is negative change. Okay, it is lost by the system. It is negative. But any gain on the system or to the system, that means some amount of pressure, extra pressure that is being applied to compress the gas. If the gas is expanding, that means it is done by the system. I mean, overall, the net effect is by the system. And net effect is by the system. So overall expansion will always give you negative work, while compression, which is on the system, will give you positive work. So you can see, if heat is given to the system, heat is positive. If it is released out of the system, it is negative. and work done by the system. In that case, expansion is happening, then work is negative. If work done is on the system, then expansion is positive. So W is greater than 0. Okay. So this is a typical convention that you always need to follow. Okay. And that's the reason why this minus was introduced. Now imagine this. If there is an expansion, V2 is greater than V1. So after integrating, everything will come out to be V2 minus V1. So if there is an expansion, definitely V2 minus V1, that makes it positive. So overall, this entire thing will become positive, and minus of positive value will be negative only. So since there is an expansion, because V2 is greater than V1, that's what we discuss. It should always be uh, the minus is always be the general formula. Okay. Clear, everybody? Any doubt here? Next. Like I said, this is thermodynamics first law. Delta U is equal to Q plus W, which is sum of heat and work done by the system. Okay. Now let me introduce to the next term known as the enthalpy. Okay. Enthalpy represent what is the overall heat content of the system. Okay. That how much amount, whatever the particles which are present, whatever the uh, matter which is present in the system, everything has certain amount of heat content. Everything has certain amount of heat content with it. Okay. That means when certain amount of temperature is provided to it, it might release some heat. Okay. Clear? So there is always a stored amount of heat in every particle, and that can be given out in the form of heat whenever it is needed. And like that, if you add all the heat contents of every substance present in the system, then that is called as enthalpy. So enthalpy is the overall heat content of the system. Mathematically, how we can write? H, which is enthalpy, can be written as U plus PV. This you will have to remember as a direct formula. Mathematically, enthalpy is always equal to U, which is internal energy, plus PV. Okay. Now, any change in the enthalpy will subject to the change in internal energy and subject to that change of PV energy. Okay. So this is about enthalpy, everybody. Clear? And I told you about heat capacities already. Normal heat capacity, specific heat capacity, molar heat capacity, and heat capacity at constant volume, heat capacity at constant pressure. Okay. So these are two terms to be checked thoroughly. So heat capacity at constant volume, how do we write it? So QV is equal to NCV delta T. Heat capacity at constant pressure, how do we write it? NCP delta T. Right? So as per first law of thermodynamics, if you are operating at a constant volume, work done is 0, then delta U is equal to QV, and QV we got it as NCV delta T. So we get a general formula, delta U is equal to NCV delta T for ideal gas. If the same thing I write it for constant pressure, delta U is equal to QP plus W. Not constant pressure, we cannot say volume is work done is 0, because there might be definitely some change in the volume. And work can be written as minus P external into dV. Okay. And if P external is nothing but pressure of the gas outside. Okay. Sorry. P external is equal to P internal of the gas at constant pressure, because since it is at constant pressure, internal, external pressure, everything should be same. Then only there will not be any movement of piston. Okay. In that case, whatever the external pressure which I have written, it will be same as the gas pressure. So I can write W is equal to minus P into delta V. Okay. And delta U is equal to QP minus P delta V. Correct? QP minus P delta V, and QP is equal to P delta V plus delta U. And we learned that delta H is equal to delta U plus delta of PV. At constant pressure, delta H is equal to, now look into this part. If you have delta of PV, I can write this as V delta P plus P delta V, correct? But if you write the same equation at constant pressure, then what will happen? At constant pressure, delta of PV is equal to, because you didn't keep this V delta P constant, so this will become 0 and it will only remain as P delta V. So that's what we have written here. At constant pressure, delta of PV is equal to P delta V. You can see it will be uh, P delta V here. Okay. And you know that delta H is equal to QP. Okay. Delta H is equal to QP, because how we can write down that? Delta U plus P delta V. Isn't it? Delta U plus P delta V. Now, QP here from this equation, you could notice it is same as P delta V plus delta U. This is what we got. That's why delta H is equal to QP. And QP, we just learned it earlier, that here you can see if you are operating at constant pressure, it will be NCP delta T. So therefore, I can equate that as NCP delta T. So delta H is equal to NCP delta T. Right? So delta U is equal to NCV delta T. And this can be used in any process. So delta H is equal to NCP delta T, delta U is equal to NCV delta T. And how both of them are related? Delta H is equal to delta V plus P delta V. If I write both of them, NCP delta T is equal to NCV delta T plus NR delta T. Because for an ideal gas, PV is equal to nRT. And if at constant pressure, no change, only change is volume change. That should be equal to temperature change. Thus, P delta V can be written as NR delta T. Now you can notice delta T, delta T, delta T will get cancelled. N will get cancelled. So what is left? Cp is equal to Cv plus R. So the heat capacity at constant pressure, how it is related with heat capacity at constant volume, that is the difference of those two will be always equal to R. But this is only valid for ideal gas. Please remember that. Because we are taking these all formulas and then deriving it. It is only for ideal gas. Next, what is Poisson's ratio? Poisson's ratio is, defined as gamma, which is equal to Cp by Cv. Okay. Cp is the heat capacity at constant pressure. Cv is the heat capacity at constant volume. So the ratio of these two is what we call it as Poisson's ratio. Now, if at all I divide, that Cp is equal to Cv minus R. So if at all I uh, divide everything by Cv, so this will become gamma, this will become 1, and this will be R by Cv. So gamma minus 1 is equal to R by Cv as well. And gamma is equal to 1 plus R by Cv. Okay, this is Poisson's ratio. So everybody, so I hope you got some idea about enthalpy, how it is related with uh, delta U, which is internal energy, and thereafter how Cp and Cv are related, and finally what is Poisson's ratio. All right, so please quickly go through it once. Start from where is it? Heat capacity. Yeah, here. Start from here. Okay, read one by one, each and every term, thoroughly read it once.